just type on here?
What are you doing? What are you doing?
We want to put down, okay, well, you do it then.
All right.
Okay, so the website, please. So we want www, presentations can be found at.
Did I spell it right?
Yep.
Okay.
www.drinc.
DRINC.
And then I need help. Well, I wrote it down on a different piece of paper.
I understand. I don't know where that can be found either. Is it at the end of that thing that's next to you? Yeah, what's the URL? Huh? .ca? There's no at? Oh, you're right.
ca.gov/DNN. DNN.
MN?
No, NN.
NN?
Yeah.
Okay.
No. That's it. And then, and also the presentations and the video of this.
Wow. Video will be coming.
Yeah.
We'll link it.
Video will be linked. Yeah.
I'll put that down at the bottom.
Yep. Yeah.
At the end.
Oh, you figured out how to print from there?
I wasn't sure how noisy it would be.
Yeah, I didn't know either.
Thank you very much for filling that out.
Thank you. Okay, if we can get back to our seats. I knew this would happen. I'd lose people. And I did. You give them a break and they leave. But these are the diehards. These are the ones that care, right? We should have had some special prize or, some special nugget of information. Your presentation, right? Okay, I'm going to give it another 2 minutes and then we'll start back up. Shall I read out that one comment we got, or is it not necessary? Or the school thing? She said that while she was sitting there, she got some. Yeah. Oh, we got another question? Oh, okay. Well, this is more for the end, huh? Okay, perfect. Perfect. Okay. Cool.
Okay, do you want left up here? Do you want down here?
Do you want roving microphone or?
Okay, everyone, we had a request, so we put up on the screen again where the presentations can be found. We'll also link the video as soon as we get that. I'm not sure how long that will take, probably a couple of days or
Yes.
so. So,
Okay, so for those of you that have asked, there's the website. And as Jim said, we'll try and link the video of these 2-day proceedings to that website as well. We're going to resume. This is the home stretch. We lost some people, but that was to be expected. You guys are here for the best part, right? Anyways, we're scheduled to go for until about 4:40, 4:45 or so. There will be some closing remarks, hopefully. Our board member, Franz Spivey Weber, had a briefing, but we'll be back downstairs. And we'll go to the next one then. So, EnviroPack Nitrate Removal Technologies from Orica. Go for it. Thank you.
Thanks. I'm Scott. I'm with Orica. We provide many technologies. Nitrate treatment is one of them. Orica is a very large company, over 15,000 employees, multiple sites across the globe. We have 3 sites for water treatment, one of which is in Denver. Orica's goal is always to combine our expertise and process knowledge to provide the most sustainable solution and access the customer's needs. We come from a very large mining background that allows us to treat a different type of water every day. So if it's potable, wastewater, process, product, recycle, or just minimizing waste, we have case studies and expertise in it. We use ion exchange, membranes, advanced oxidation, media filtration, and we have a lot of experience in residuals management. So there's a lot of technologies involved in that. Today we're going to talk about nitrate. In traditional ion exchange that's been mentioned, you can get multiple contaminants. We have certain technologies with our upflow design that we can blend resins. This allows us to do hardness and organics, hardness and nitrate. Maybe we're doing bromide as well. We can really blend a lot of different of our resins together to try and meet multiple challenges at the same time. We also have, we started as an ion exchange company, which has put us in the same boat as everyone else here. There's a brine waste challenge. So we've softened the waste, we've evaporated, and we've concentrated it with nanofiltration. So there's always another option to just squeeze a little more out of that residual. Again, you know, we have studies all over the globe. We have over 60 installations, and some of the same goals are listed here as we've been going over. So as for ion exchange, we have an advanced ion exchange treatment solution. We remove organic and inorganic contaminants, nitrate, bromide, arsenic, chromium-6 we talked about, ammonia, lead, hardness, other metals. We try and minimize our footprint. It helps cut costs on the building costs. We're the leaders in process efficiency. We received 2 consecutive Green Technology Ribbon Awards at the ACE show from the American Waterworks Association. Here's a picture of some of our installations. So for North America, we have a footprint and a lot in the southeast. Like I said before, we have about 55 plants. This is about a year old, so we're up to closer to 60, and next year we're going to go over 1 billion liters per day in capacity. Here's a quick slide on nitrate removal using ion exchange. The quaternary amine structure is in the chloride form. You can use other regenerants, but chloride is the cheapest regenerant. As the nitrate contacts the bead, the nitrate exchanges with the chloride, and then you can reverse the process in a high concentration of chloride or other regenerant. Our specific resin is the MIX resin. It stands for magnetic ion exchange. Our beads are about the fifth or a fourth of the size of an average conventional bead. This provides more surface area, and usually this allows us to do an upflow design in a mixed bed with high surface area and fast kinetics. I'll talk about that more later. This is the selectivity chart that has been seen in different iterations throughout the day. So you can see chromate, organics, perchlorates are on there, arsenate, and nitrate is what we're talking about today. The MIAX high rate process is an upflow process. The water comes in the bottom, and then there is agitation or a distributor for mixing energy. What this does is it keeps the resin in suspension. There's a separation zone, and then the treated water goes out the top of the vessel. This can be pressurized or atmospheric. We have a lot of experience in surface waters where turbidity is not a factor. There's a slipstream regeneration, as Chad mentioned earlier. A fraction of the resin, maybe up to 5%, goes out into a separate process vessel where brine is contacted with the resin. The contaminants come off. It's back in the chloride form or whatever regenerant you use. And then it's rinsed. And we can have as low as 0.1 to 0.3% outputs in terms of waste. The countercurrent MIAX process is one of the solutions that I'll show you today. It uses two vessels. They're both upflow. In the case of the case study, it's two pressurized vessels. It's almost like a lead lag design, except your lag is in front. So the resin moves from the right side to the left side, where the cleanest resin comes in at the right, and then it's partially exhausted and then moved into the vessel on the left. What that allows you to do is grab the easiest contaminants on the partially loaded resin in the first chamber, such as your sulfates, your organics, and then when you have really clean resin in your second contaminant or second chamber, there's only pretty much nitrates and harder to remove anions in there with the most capacity in the resin in the second chamber. So the idea behind this is you get a higher efficiency of removal of hard-to-get contaminants. This is an example of a 400 GPM system. This is an atmospheric design. On the right is your reactor vessel, and then on the left are your resin regeneration and salt containing process tanks. This is a 14.5 MGD plant. On the upper left, that is the concrete basins for reaction. In the middle, the resin process tanks, and then on the right, your salt handling equipment. And then we'll get to the smaller scale here. So the advantages of fluidized bed ion exchange is that there's no blending requirements. You don't need the online analyzers. We have a system that works on field instrumentation only, and this ends up with no nitrate dumping or any other contaminant dumping, and you can apply it to higher turbidity situations. And the way we control it is we control the regeneration slipstream as the nitrate load increases due to seasonal or partial use situations. We can increase the amount of salt and resin processed to increase the capacity on the resin for when the nitrate does start to spike on the raw water. This is the first case study. This is Indian Hills Water District. It's on the outskirts of Denver in a small rural community. It had a history of farming. There's about 11,000 people there, and they average 1,100 people and 45,000 gallons a day. So this is a surface and groundwater distribution system. The surface water has been in short supply. There's been droughts in Colorado, and they supplement their water with the groundwater. So they're in violation if they use that solely, but they try to blend to get into compliance. So this also lines up with our challenge of doing a 50 GPM system and costing it. So keep that in mind as I go through it. Their challenges to us was 50 GPM of flow. This actually has a turn down to about 5 gallons per minute. So you can go 5 to 50 and reduce the nitrates by 50%. So this does not have a wastewater treatment facility. All waste is tanked off, but as you can see, it's relatively close to Denver, so it's easy to find a place to put it in a wastewater plant. So we came in with our countercurrent upflow design, and the treated water quality, the raw influent average is 12 to 16. 14 is about 60 ppm as nitrate, and then the treated average is 5.4, which is closer to about 25 as nitrate. We also have other anions, the DOC, that's a potential for disinfection byproduct issues with your chlorinated fractions of disinfection byproducts, the chloroform and THMs, particularly in that case. We do remove sulfate, and then this is a relatively high hardness water, which our resin is pretty resilient against scaling, so we don't have to soften the brine, which adds to the efficiency. We did a pilot study. This shows the same raw water coming in, same nitrate effluent coming out. We tried it with one reactor and with two. We saw a little bit more removal with the two reactors. We also tried to demonstrate that if we spiked the water and put the nitrate as a nitrogen concentration up to 25, we were able to increase the regen rate and keep the controlled effluent in their target about 5 to 6 on average there. The system has a minimal footprint. The client is looking to put in an online nitrate analyzer just for monitoring purposes. The system runs on a field colorimeter. It's a Hawk test and tube kit, and the operators test it once a day. It's two guys. One guy's the fireman. The other one is the wastewater distribution and drinking water guy. There's a 2,000 gallon storage tank, and we're using about 3,000 pounds per million gallons output. There's no large salt handling. This is a mountainous area, so they use bags of salt, and the system was designed for that. We also have 2,800 gallons per million gallons of weights, which puts us at 0.28%. To finish off the system, there's a 1 micron bag filter and then free chlorine. This cost about $150,000. This was in 2008, I believe. The resin cost, as an ongoing basis, you probably have to replace it every 3 to 5 years. Salt's relatively cheap in the area, so $100 a ton. And then there's minimal power. About 1 kilowatt hour is probably just to keep the lights on and keep the PLC going. This is a basic system, painted carbon steel vessels, FRP, HDPE process tanks, no online instrumentation, and 100% redundancy. So to keep that reliable system, we have a PLC. We had to do 100% redundancy for the state. It can run on one contactor or both to get extra nitrate removal, and then there's 2 regeneration tanks. Our second case study is the county of Brant in Ontario. It's halfway between Buffalo and Toronto. This was a bid that we replied to, and it's about a 792 GPM system in total. Associate Engineering was the lead, and it was a groundwater system, and they spec'd nitrate-specific resin with automatic blending, including Nitrotax Hawk analyzers. They do have sewer there. The 50 liter per second distribution was set up with 3 20 liter per second contactors and a 10 liter per second bypass that could go up to 50 liters per second. They had a requirement of 24 hours before a vessel would regenerate, and they also gave us the 20-year nitrate loading for the capacity design. We had to blend to an effluent nitrate of 3 as N, or close to 15 as nitrate, and then we could not exceed 3.5 as N. We did have a process warranty on there for a year, and we also had a warranty where if it did alarm, we'd have to show up. So we haven't shown up yet. We went in with an alternate bid of the split flow countercurrent regeneration design. I'll go over that in a minute here. So it's still a top-down conventional ion exchange system, fixed bed. You go in the top, you come out the bottom, and then as we alluded to earlier, that the nitrate really loads on the top. So the way this is done is we reuse the brine and we regenerate the top third of the media. And you can go through multiple cycles of that before you have to regenerate the entire bed. That allows for waste and salt savings. So a strong base anion type 2 resin selectivity with nitrate specifics kind of rotates the selectivity chart a little bit, but it pushes nitrate and sulfate a little closer together. So We don't have a lot of water quality on this, but the nitrate is continuously monitored. It comes in at 11, and then out of the vessel it's 0.2, and with the blend it's 3. There's a little bit of DOC and sulfate, and then the hardness in silica is very high, almost in the falling range. So we've been able to not have any issues on that. And then there is softening on the brine preparation. So this system has 5 online Hawk Nitrotax analyzers. That adds a lot of cost. Each vessel has their own analyzer. The bypass has an analyzer, and the blended has an analyzer. We're able to get the salt use down to 900 pounds per million gallons, and the waste to 3,200 gallons per million gallons, 0.32%, using pretty much conventional ion exchange. Of that breakdown of the waste, 0.14% is high conductivity. That's where the majority of the nitrate is. And then 0.18% is the low conductivity waste, your backwash water and your fast rinse. There's a resin trap and then free chlorine to complete the system. This one came in high just because of all the site requirements. We had to use specialized valving, specialized instrumentation, nitrate-specific resin when it didn't really call for it. However, you did get some operational benefits on that. We had to do stainless steel face piping, and it was in a remote area, so your salt price is well over 100 per ton, as it is in Colorado. It's 225 a ton. We estimate that the resin will last 7 to 15 years. The resin is probably twice as expensive as conventional strong base anion resin. The nitrate specific doubles the price. It's just not used in large enough volumes for the economies of scale. And then almost no power is used for our portion of the system. The well power is probably the majority of the power for the system. So this is pretty much just keeping the lights on and running a 2 horsepower pump for 30 minutes once a day. We did have a little reliability. This is a 3 by 50% system. That it's essentially 2 vessels on and 1 in regeneration or standby. The automatic blending is achieved through the nitrate PID loops. We did have a performance warranty. We had duty standby pumps on the salt system. If you look on your left, there's your salt tank, the salt preparation skid, and then on the right is your 3 vessels. This does have remote monitoring. We can go on our laptops or our iPhones and control the system, and it's been very helpful for the first few months as you're trying to train operators and get them accustomed to a new system besides just chlorine. You can walk them through it. Any questions?
We're assuming that it takes a T2 to operate the system?
You know, I'm somewhat unfamiliar with Ontario legislation, but I believe it would be the same as any conventional ion exchange system.
I'm sorry if I missed it. Were you sending the waste brine in the Colorado case?
That went to a 2,000 gallon above ground storage tank, and then it was trucked off to a nearby facility.
A nearby facility is a municipal wastewater treatment plant?
Yes. It's probably 20 miles outside of Colorado, so it's very easy to get it to a local municipality.
Okay, thank you.
Alan Miller, Regional Water Board. I think one of your slides said there was no sort of nitrogen reject or something like that, maybe an earlier slide than where you're at right now?
I think I did mention that
I didn't understand that.
you could split the waste. Is that what you meant? No, there's usually you know, always a concentrated nitrate stream with the salts. We do have the ability to evaporate that waste stream or concentrate it with nanofiltration. In a nanofiltration case, you could reuse a portion of the salt and concentrate your waste. It's the same idea as some of these nitrate destruction technologies. It's high energy, but you use nanofiltration to keep the salt and water and concentrate up all the other anions and whatever else is that won't pass through a nanofiltration membrane.
Hi, David Freeze, APT Water. Question is, I thought I saw some pumps and agitators in there, and if you could comment on just horsepower, and then maybe you could clarify on the power use, what are the units, because it's kilowatt hours, but there's got to be a time basis, so I didn't know what that was, what that meant.
Sure. As for the units, it's more of an average power use. You're right, certain things are going to cycle. In terms of horsepower on a fixed bed conventional ion exchange system, the valves are barely turning. We have motorized electric valves on this system, and then there's a 2 horsepower pump in the brine preparation stage. So it uses system water, distribution water, so it's already at pressure, and then it blends with an adductor, and then to drive from the saturator to the vessel and blend with that, there's about a 2 horsepower pump that runs for 20 minutes each time it does a regeneration. So 20 minutes a day you're running a pump, the rest is all just controls. On the other system, to keep a fluidized bed, we have a recirculation pump here. And what that does is it takes the effluent and puts it back through the bottom to keep the resonant suspension. And for a 50 GPM system, that can probably be handled by a 1 to 2 horsepower pump. And depending on the influent flow, it's kind of if we have full flow, we don't need the pump. If we have zero flow, we need the pump at full speed. So you're using a percentage of that. So that's your major horsepower draw on a fluidized system is probably an average of half the percentage of the. So if it's a 2 horsepower pump, you're probably averaging 1 horsepower on it. In this case, I believe it's a 5 horsepower pump because it's doing both vessels. So you'd be adding 2.5 horse plus the 1 horse or the 1 kilowatt hour on average for the controls.
Any other questions? Any on the web? Nope. I thank you.
Thanks.
So next I have Eugene from CDPH.
You're going to load yours up? 'Cause I don't know which one you want to load first.
And while we're loading that up, I want to remind everyone there are goldenrod colored evaluation forms at the back of the room. They handed a bunch out. If you could please fill those out and either leave them at the back of the room or LaFay she's at the back of the room, she can get them from you. So please fill those out so we know how we've done and what we could do differently or how useful this was for you. Thanks.
Hello everyone again, good afternoon. This is the final technology that we're going to present today that is ready to go, hopefully. The one that we're presenting today is selective electrodialysis. Unfortunately, the vendor for this product is based in Israel and is the Jewish New Year, so they're unable to come to our workshop. But they have graciously sent me some of their presentation slides, and I'm going to present some of them as part of my presentation. So the basic treatment scheme here we have is selective electrodialysis. What that means is actually it's a membrane process, but instead of like reverse osmosis where you're forcing your raw water through a membrane, you're actually only drawing some of the contaminant through the membrane, and majority of the water just pass through the main channel for the membrane. So in this particular case for selective electrodialysis, you use anion and cationic selective exchange membranes. Selective electrodialysis is not a direct filtration method, as I said, so hopefully the pump costs will be lower than when compared to reverse osmosis where you're trying to push the water through the membrane. The pretreatment is needed for constituent that may foul the membrane. As with anything, if the membrane's fouled, it won't work. So here's a basic schematic of what electrodialysis looks like. This is for the membrane rack. These pictures are available in the UC Davis technology report. And you see that here, right here in the middle, where the concentrated stream is, that's where the reject water will go. And here is the raw water where it's just passing through. And on the two ends of these stacked membranes, there's a cathode and anode on the left and right side of the picture that you can see. So I'm going to switch over to the cartoon, which actually explains this process really well. So as you see right now, the blue channel where you have the little ping pong balls going through, that's your raw water stream. You have all your contaminants of different kind. You have your nitrate, calcium, chloride, sodium, and whatnot. So the membrane they have here is nitrate selective. So by turning on the technology, it's not working. You see that the ions, the positive and negative, start attracted to the side of the membranes. And you can see the nitrate, which is the gray ball, majority of them will get into the reject channel, whereas majority of the other ions is just passing right through in the main channel. So this is one way for us to concentrate nitrate and have a reject stream that is mostly nitrate and does not have very high TDS, because majority of the water just passes right through. Okay, so the potential treatment benefits for this one is the treatment objective is we want to maximize water recovery with the minimum amount of energy and chemical usage, as with any technology that we're trying to do. In this case, there's a potential here because you have lower pumping cost compared to reverse osmosis. So that's a benefit. The selective electrodialysis process just removes the nitrate, so the TDS remains in the treated water, like I mentioned earlier. And since the TDS is concentrated, the TDS concentration in the concentrate stream is so much lower, there's a potential for you to use that concentrated stream somehow. And one possible way is the concentrate can potentially be used for irrigation without the salinity that adversely affects plant growth that you have with RO. So this is a good potential for SED. So big disclaimer. I'm presenting the slides for the company. We are not endorsing this product. It's only for informational purposes. So I'm just going to go through that. So the company, the product is Shakun and Benui. They are a company based in Israel. They have these products, actually a couple of them in use in Israel already, where they have a big nitrate problem as well. So their company is one of Israel's largest housing engineering construction group. SWRCB, it's their water arm, and they build and design water plants in Israel. They have a couple plants. The Hadera desalination plant is one of them. They have a groundwater remediation and reclamation plant, and then they also have municipal water and sewage services. So the nitrate treatment, these are their talking points. The value proposition is that SED is a electrodialysis-based technology. ED is well-known nitrate technology with the EPA list as the best available technology. It removes selectively up to 70% of the nitrates and only 5% of the sulfate. The technology is inert to silica. Its low energy consumption compares to commonly uses less than 0.57 watts per 1,000 gallons. They have standard modules with 330 membrane pairs that can treat up to 440 gallons per minute. And they have standard modules with 120 membrane pairs that can treat up to 154 gallons a minute for feed water. Their goal is having a 95% recovery rate and negligible chemical use. The chemical that they have told us that they need to use is put a little bit of acid in the concentrate stream so that prevents the scaling of the nitrate or any concentrate that they have on that side. And the membrane, they claim that is already NCNSF 61 certified, but I have not verified that. So same as the diagram that was shown earlier, The cation exchange and selective anion exchange membranes are arranged alternatively between the electrode cells. So you have the main channels, and then you have the reject channels in between. The selective anion membranes do not allow divalent anions, such as sulfate, to pass through the membrane, allowing relatively low concentrate TDS and low precipitation potential of poorly soluble salts. The electrodialysis transfers ions by using direct current as driving force, creating product water and concentrate streams. And here's some case studies that they have provided us. The SED nitrate treatment plant at the Nes Ziona well E. The drinking water standard for nitrate in Israel is 70 ppm as nitrate, so it's much higher than ours. To save the water expenses, the city examined Arrow and SED as the nitrate treatment alternatives, and for their cost that they have found SED to be cheaper. So they have done quite a bit of study, and then they actually installed the treatment plant, and it came into operation in 2011. Here are some examples and results of what they can do. As you can see, the raw water coming in from this well is around 90, and then the effluent they can consistently meet around 40 to 50, but that's based on a standard of 70. And they have been working with us here in the States because they're proposing to try to enter our market, and they're working with one of the larger water utilities in California. And they have done some baseline pilot studies in laboratory environment, and they're able to mimic the same performance here so that we are able to do similar work when they actually try with real California water. They actually ship barrels of water from Israel to here to demonstrate that the pilot unit actually, when they do the bench scale, it mimics full-scale operation. And that's the tricky part about using the SED process. Is you really cannot pilot it. You either have to buy the whole unit and start running it. And the next best thing to piloting is running a laboratory-based experiment. So one more disclaimer, just in case. The preceding slides was a sponsored message. But anyway, so back to our main diagram for the family tree of treatment technology after all of this. As you can see, we have lots of treatment options available. I think it is evident from all our discussion, treatment residual handling is one of the biggest problems with nitrate treatment. There are a lot of technologies that's efficient and effective in reducing it, and we have gone through in the last 2 days on different methods of dealing with residual. And probably our solution is what's in the middle. We need a lot of hybrid systems, different ways of solving the nitrate problem. And that's it for my presentation. Thank you.
Oh, there's a question at the back of the room. Oh, there's a few questions. Cool.
Thank you. I'm Kathy Swanson with Siemens Water, and I just wanted to put in a 20-second plug for what we can also provide in terms of nitrate solutions. We can do an off-site ion exchange regeneration, and the advantage of that is we are regenerating at our facility. We take care of the brine, and we just exchange vessels at the water purveyor's site. So you get the benefits of ion exchange and without any brine or really operations that is necessary. I ran a little bit of the cost last night after seeing some of the presentations. You know, depending on if you want to rent or if you want to purchase, you know, your capital outlay is very similar to what a lot of these other systems were, probably like the 250 to 300,000 ballpark. And the operational cost, although is a little bit higher because there's a lot more transportation, somewhere between $15,000 to $20,000 a month operational. If you go with rental vessels, obviously that's a little bit different. But if you have questions, let me know. You know, we can certainly do breakdowns for individual sites.
Thank you. There's, Chris, there's one at the very back, and then I've got one up here.
Hello, I'm Sharia Ramesh with Cal Water. And Eugene, you had mentioned that the concentrated waste was only high in nitrates and not in chloride. So I guess I'm posing the question to the regional board. Is that something that can be used in other uses? High nitrate water can be really valuable to certain other processes. So just something to consider as alternative options.
Alan Miller, Regional Water Board. In the electrodialysis, is it the selectivity of the membrane that allows only nitrate to go